Okay, hello everyone, welcome back. All right, so today is Thursday, September 10th. Okay, we're going to finish up chapter 1. 1.11 is optional, so we're going to skim over that. The homework for chapter 0 I'm still working on. That's taking a while. The grading is slow this month, remember. So next week we're going to start chapter 2, although that's not going to be on the chapter 1 homework, obviously. Your next homework is going to be due on the Friday, September 18th. That's when the homework for chapter 1 is due, for chapter 1. All right, any general questions about the schedule? Any general questions? All right. Okay, any questions? Any questions? Okay, so let's go ahead and start. Go ahead and chat.
Hi, everyone. We're going to revisit the issue of symmetry in section 1.7, in particular, the symmetry of even and odd functions. Let's go back to section 1.3, where we introduced even and odd functions, when we studied basic graphs and symmetry. We looked at the squaring function given by y equals x squared. And this was an even function. We assumed that the domain was the implied domain of all real numbers. The domain of f was assumed to be all real numbers. Remember, in order for a function to be even or odd, the domain must be symmetric about 0. R itself is symmetric about 0. Now, what was true about this squaring function? Not only was its domain symmetric about 0, but whenever we input a pair of opposite values for x, like 3 and -3, we got the same function value, the same y coordinate. In this case, 9. The square of 3 was 9, and also the square of -3 was 9. Meaning that on the graph of y equals x squared, the point 3,9 was on the graph, which meant that the point -3,9 was also on the graph, because f is an even function. That's a demonstration of symmetry about the y-axis. Anytime xy is on the graph, opposite xy is also on the graph. Anytime xy is on the graph, opposite x, comma y is also on the graph. A function is even, in general, if and only if you input opposite values for x, whenever x is in the domain of f, the function values are the same. F of opposite of x equals f of x for all x in the domain of f. Graphically, that means that we have symmetry about the y-axis. For every pair of opposing x values in the domain, the y values are the same. Here's a proof. We want to show that f of opposite x equals f of x. Well, when you square the opposite of x, you just get x squared, which was f of x. F of opposite x equals f of x for all x in the reals, which is symmetric about 0. So the squaring function was a basic example of an even function. By the way, constant functions are all even functions. Like, for example, the function given by f of x equals 3, that's even. X equals 2 gives 3. Also, x equals -2 gives 3, for example. The graph is symmetric about the y-axis. All constant functions are even. I don't care if 3 is an odd integer. All constant functions are even. The 0 function, in fact, is both even and odd. Now, what about odd functions? Well, the identity function, given by y or f of x equals x to the first, that was a basic example of an odd function. That was symmetric about the origin when you graphed it. Another one we looked at was the cubing function, given by f of x or y equals x to the third, or x cubed. That was a basic example of an odd function. Again, the domain is all reals. Domain is all reals. Now here, remember, the domain has to be symmetric about 0 in order for a function to be either even or odd. And why is it odd? Because when you input opposing values of x, like 3 and -3, you get opposing values for y. Positive 27 versus -27. Or if you take more humble numbers, if you input 2 and -2, you get as the cubes, the y coordinates, 8 and -8, which are opposites. If you input opposite values of x, you get opposite values of y, opposite function values, as outputs. If 2, 8 is on the graph of an odd function, then -2, -8 must also be on the graph of an odd function. In general, if xy is a point on the graph, then for an odd function, the point opposite x, opposite y must also be a point on the graph. For example, 2, 8 and -2, -8. In general, in order for a function to be odd, whenever you input opposing values of x on the domain of f, the resulting function values are opposite. The y-coordinate at opposite x is the opposite of the y-coordinate at x. The function value at opposite x is the opposite of the function value at x. And this is indicated graphically by symmetry about the origin. If the graph is rotated 180 degrees about the origin, we get the same graph. Like for the graph of this rising snake, y equals x cubed. Rotate it 180 degrees about the origin, you get the same graph. Here's a proof. Again, if you want to prove that a function is even or odd, if you're given the rule for f of x, you want to analyze f of opposite x. When you substitute x with its opposite, this is a substitution, remember. When you substitute x with its opposite, substitute x with its opposite, look here, you get the cube of opposite x, which ends up being the opposite of x cubed, because the cube of -1 is -1. And that's actually the opposite of the original function rule here. F of opposite x is the opposite of f of x for all x in the reals, the domain. So now we're going to talk about even functions and odd functions more generally in section 1.7.
Okay, that was a review from 1.3 on even and odd functions. Any questions? Any questions? Okay, feel free to chat questions. Let's proceed.
Hi, everyone. Let's continue with our study of even and odd functions. This will help us a lot. The fact that linear combinations of even functions are even and linear combinations of odd functions are odd. What's an example of a linear combination of two functions, f and g? Here's an example. 2 times f plus 5 times g, that's an example of a linear combination of f and g. Anytime you have a number times f plus a number times g, that function will be a linear combination of f and g. In fact, the zero function is always a linear combination. Now, if f and g are both even functions, then 2f plus 5g will be even. If f and g are both odd functions, then 2f plus 5g will be odd. In particular, the sum or difference of even functions will be even. The sum or difference of odd functions will be odd. A constant multiple of an even function will be even. And a constant multiple of an odd function will be odd. So for example, well, first off, here's a proof showing that the sum of two odd functions is also odd. Don't freak out about this, but here's a proof. Let's say that we consider the graphs of y equals x and y equals x cubed. These both represent odd functions. Their sum, given by the rule x plus x cubed, will also represent an odd function. You can get this from a table of values or from a graph. In blue, we have the graph of y equals x. In red, we have the graph of y equals x cubed. In brown, we have the graph of y equals x plus x cubed. The odd property, where we have symmetry about the origin, is maintained. The blue, red, and brown graphs are all symmetric about the origin. All three of these are odd functions. So for example, if we take y equals x cubed, this graph is an odd graph. I could multiply it by 2, by 3, by -3. All these graphs will be symmetric about the origin. These all represent odd functions. I can multiply x cubed by any real number, and I get an odd function, even the zero function. If I have y equals x plus x cubed, that's also an odd function. We have symmetry about the origin. In fact, I could go y equals cx plus dx cubed, and I can slide over real values for c and d. So c could be various values, d could be various values, and we retain that odd property. The graphs are still symmetric about the origin. So again, any number times x plus any number times x cubed, that's going to represent an odd function. A number times an odd function plus a number times an odd function, that's going to get us an odd function. Linear combinations of odd functions are odd. Likewise, linear combinations of even functions are even. Let's do cx squared plus dx to the fourth. Get these W-type graphs. Even, symmetric about the y-axis. Next up, we have some easy rules for figuring out whether polynomial functions are even, odd, or neither.
All right, questions. The even and odd properties, and some functions are neither. Questions.
Hi everyone, how can we tell if a polynomial function is even, odd, or neither? I have a bunch of rules in this box here, but let's go straight to some examples. I claim that the function f, where f of x equals 3x to the fourth minus 7x squared plus 1, is an even function. Why? First of all, I like the form of this rule here. Notice that it's a polynomial written in descending powers of x. I don't have any squares of binomials or stuff like that, for example. And bear in mind, I could have a polynomial in x or t or whatever. If you see something like a 0x cubed, you can go ahead and kill it. We want non-zero coefficients. Now, first, I'm going to look at 3x to the fourth minus 7x squared. I think you'll believe me if I tell you that that represents an even function. Take a look at these exponents. A 4 and a 2. These are both even integer exponents. X to the fourth and x to the second represent even functions. Take a look here. Our old friends, y equals x to the second, that's a parabola. Y equals x to the fourth, that's another bowl. Both of these graphs are symmetric about the y-axis. These both represent even functions. And remember, a linear combination of even functions is even. 3 times x to the fourth minus 7 times x to the second, that will also represent an even function. Y equals 3x to the fourth minus 7x squared in green, that's going to represent an even function. Again, we have symmetry about the y-axis. So you should believe that 3x to the fourth minus 7x squared gives an even function. What might creep you out is the +1. How do we retain the even property? Well, let's try this out. Y equals 3x to the fourth minus 7x squared. What does the +1 do? What does the +1 do? It raises the graph by 1 unit. But you see, we still have symmetry about the y-axis. In fact, I could subtract or add any real number. I could add any real number c, put in this slider, and the graph will stay symmetric about the y-axis. We're just sliding this w graph along this y-axis. So you can add any constant to this over here, and you'll still have an even function. If you want to think in terms of exponents, look at it this way. Think of 1 as 1x to the what? 1 is 1x to the 0, because x to the 0 is basically 1 itself. For now, we think of 0 to the 0 as 1. In polynomial theory, we often consider 0 to the 0 to be 1. So if you look at this as 3x to the fourth minus 7x to the second plus 1x to the 0, notice that all the exponents on x are even. We have the nice descending powers form. So it's not a surprise that the corresponding function is even. These even exponents, 4, 2, and 0. It doesn't matter what the coefficients are. I don't care that 3, -7, and 1 are odd integers. That doesn't matter. In fact, when you look at this odd integer 1, actually, because that represents a constant function, remember, all constant functions are even. All constant functions are even. Here's the graph of y equals 3x to the fourth minus 7x squared. What's the graph of y equals 1? It's that flat line, that red flat line, also symmetric about the y-axis. When you add these two guys together, put a +1 over here, you still retain the even property. The green graph plus the red graph is the purple graph. You still retain the even property. All constant functions are even, because you can pull this stunt. 1 is 1x to the 0, 2 is 2x to the 0, pi is pi x to the 0, and so forth. That's one reason why we say that non-zero constant terms have degree 0. Non-zero constant terms have degree 0. So a 1, a 2, a 3, a pi, a negative pi, they all have degree 0. 0 itself has no degree. In fact, the 0 function is both even and odd. So this here gives us an even function, whether there's a +1 or not. In fact, you can add or subtract any real number. Next up, an example of an odd function.
Any questions thus far? Any questions thus far? Because if you understood that, then I think you'll be fine with the rest. But any questions thus far? The +1 retains the even property. That confuses people. The +1 is +1x to the 0. 0 is an even exponent. Questions?
Hi, everyone. If f of x equals 4x to the fifth plus x, then f is an odd function. Let's go to Desmos. How do you graph y equals x? The identity function is that slanted line. How do you graph y equals x to the fifth? That's that rising snake. Y equals x is kind of a dead straight snake. Y equals x to the fifth is a tall, proud snake in blue. When you add them, y equals x to the fifth plus x. Notice the odd property is retained. The red graph, the blue graph, the red graph, the blue graph, and the green graph are all symmetric about what? They're all symmetric about the origin. They all represent odd functions. And by the way, if 0 is in the domain of an odd function, and since these are polynomial functions, 0 is in the domain, all real numbers are in the domain, then the point 0, 0, the origin, must lie on the graph. If 0 is in the domain of an odd function, then the origin must lie on the graph. Because when you rotate 180 degrees about the origin rotates onto itself. Now, here I asked about y equals 4x to the fifth plus x. Y equals 4x to the fifth plus x in black. Still, that retains the odd property. And it again goes to the origin. This is the guy I ultimately cared about. But again, a linear combination of odd functions is odd. 4x to the fifth plus x to the first, that represents an odd function. Notice I said 4x to the fifth plus x to the first. We can think of x as x to the first. And if you look at this polynomial written in descending powers of x, the exponents on x, the 5 and the 1, these are both odd integers. And when we look at the exponents, we do think in terms of odd integers versus even integers. The 5 and the 1 are both odd integers. Therefore, f is an odd polynomial function. And we have symmetry about the origin on the graphs. Now, question. What happens if we add or subtract a 1 or a 2? Well, then we get something like what we see here. In example 5, let g of t equal t cubed plus t plus 1. Is g even, odd, or neither? Well, let's check it out. When you look at y equals t cubed plus t, y equals t cubed, our familiar snake, plus t. We retain the odd property, symmetry about the origin. All right, so this here represents an odd function. But what about that plus 1? Y equals t cubed plus t plus 1. What happens? The graph goes up 1 unit, but the blue graph, is that symmetric about the origin? The answer is no. It is symmetric about this y-intercept at 0, 1, but that's not the origin. Remember, if 0 is in the domain of an odd function, the graph must go through the origin. Now, 0 is in the domain for this blue graph, but 0, 1 is the y-intercept. If you try to rotate it 180 degrees around the origin, you get 0, -1. That point cannot also be on the graph because otherwise we'd fail the VLT. So again, if 0 is in the domain of an odd function, the origin must be on the graph. This is why if you add 1, 2, 3, subtract 1, 2, pi for that matter, if you add or subtract any non-zero constant, I guess I should go plus 1, plus 2, plus 3, minus 1, minus 2, minus pi. These do not represent odd functions. So the odd property is more delicate than the even property. Remember that the even property is retained if you add or subtract a real number, 1, 2, pi, whatever. But the odd property is destroyed if you try to add a 1, a 2, a pi, or subtract a pi. You destroy the odd property. It's more delicate. Because if you try to add a 1, for example, you're moving the graph away from the origin, and that's dangerous for an odd function. Well, what about the exponents? Here we have t to the third. Okay, that's odd. T to the first. Okay, 1 is an odd integer as well. But wait a minute. 1 is 1t to the what? It's 1t to the 0. And 0 is an even integer. T cubed represents an odd function. T to the first represents an odd function. But 1 is a non-zero constant function. It is even and not odd. I don't care that 1's an odd integer. 1, 2, 3, pi, negative pi, they all represent even functions, not odd functions. The 0 function is both even and odd. But here's the problem. The exponents are a mix of even and odd integers. Or I should say odd and even integers, which means that we have the neither case. The function is neither even nor odd, because look at this graph here. Y equals t cubed plus t plus 1. Look at this blue graph here. It is not symmetric about the origin, so the function is not odd, and it's not symmetric about the y-axis, so the function is not even. It is neither even nor odd. if you try to add 2, 3, subtract pi, none of these are either even or odd. They're neither. We have the neither case. Next up, we'll talk about the proofs. How can we prove that a function is even, odd, or neither?
Any questions? These are the shortcuts for figuring out whether a polynomial function is even, odd, or neither. So there are fairly straightforward rules there. Be careful. Next, I'll do the proofs. And it's not so much that, well, on the homework, here's the deal. It's not that you have to make it super formal, but be prepared to think along these lines, right? Okay, questions.
Hi, everyone. How can you prove that a function is even, or odd, or neither? Or what if you don't know? Here we have a rule for f of x. Now, if you wanted to do an even-odd analysis, what should you consider? F of what? F of what? We want to consider opposite inputs. We want to know what happens if we input opposite values into the function. So we consider f of opposite of x, and we consider what S word. We perform what S word? A substitution. We substitute x with the opposite of x. Make sure to put grouping symbols. So f of opposite x is 3 times the opposite of x, that's to the 4th power, minus 7 times the opposite of x, that's to the 2nd power, plus 1. But wait a minute. What impact do the 4 and the 2 have on these negative signs or opposite signs in here? Well, the 4th power of -1 is +1. The 2nd power of -1 is +1. Basically, these signs are destroyed by the even integer exponents. So we're basically left with 3x to the 4th minus 7x squared. We can ignore these in here. We have 3x to the 4th minus 7x squared plus 1. And we get the same rule as before. 3x to the 4th minus 7x squared plus 1. What happened? When we substitute x with its opposite, well, the even exponent just killed these -1 factors in here, and the +1 out here didn't care. It wasn't impacted by this at all. It just stayed out there. So f of opposite x equals f of x. This is true for all real values of x, which was the domain of the function, and R is symmetric about 0. Remember, for an even function, we need the domain to be symmetric about 0. The same goes for odd functions. Therefore, the function is even. QED, end of proof. Now, how can we prove that this function here is odd? F, where f of x equals 4x to the 5th plus x to the 1st. Well, again, we consider f of opposite x. We consider opposite inputs. Again, we think of what S word. We substitute. Again, we substitute. We're substituting x with its opposite, the opposite of x. So we have 4 times the 5th power of opposite x plus opposite x. This time, however, unlike before, what happens? These guys pop out. The 5th power of -1x is -1x to the 5th. And then -1 times 4 is -4. So basically, the negative sign here does pop out and changes the sign here from a +4 to a -4. We're going to see that odd functions tend to do that. Over here, once again, this opposite sign, this -1 factor pops out, and we end up with -1x over here. The plus sign basically flips to a minus sign. So we get here -4x to the 5th minus x, which is the opposite of 4x to the 5th plus x. It's the opposite of this original expression over here. So f of opposite x is the opposite of f of x for all x in the reals. R is the domain of the function. R is symmetric about 0. Therefore, we have an odd function. QED, end of proof. Bear in mind, if we had a +1 out here, if we had a +1 out here, if we had a +1 out here, then this would have been messed up because there's no opportunity for the plus sign to become a minus sign. This helps explain why if you add a 1, a 2, or a 3 or something, you destroy the odd property. Speaking of which, what about this neither function here? G, where g of t equals t cubed plus t plus 1. Well, there are a couple ways you can approach this. One way is to do what we've done before. Substitute or replace t with its opposite. So consider g of opposite of t. Replace t with its opposite. We get the cube of opposite t plus 1. We get this over here. And here's the thing. Is this even, odd, or neither? Could this be an even function? Is this equivalent to this over here? Is g of opposite t equivalent to g of t? Doesn't look like it. G is not even because g of opposite t is not equivalent to g of t on the domain. Could this be an odd function? Well, does it look like this is the opposite of this over here? Well, we have a minus sign and a minus sign, but the +1 stays a +1. Similarly to what I discussed before, the +1 had no opportunity to flip sign. So g is not odd because g of opposite t is not the opposite of g of t either on the reals. So that means that g is neither. But here I'm kind of going by looks. I'm saying that this over here doesn't look like it's equivalent to or the opposite of the original. To be a bit more precise, we should consider a counterexample. For example, what happens if we plug in t equals 1 and t equals -1? So let's consider g of -1 and g of +1. G of -1 is -1. G of +1 is +3. Right here, I know that g is neither. G is neither even nor odd. And how do I know that? Just from this counterexample. Well, here's the thing. If g were an even function, if g were even, then g of -1 should equal g of 1. But -1 does not equal 3. The outputs are not equal. So opposing inputs do not yield equal outputs, therefore g cannot be even. Likewise, if g were odd, then g of -1, remember the domain is all reals, g of -1 should be the opposite of g of 1. But wait, -1 and 3 are not opposites either. Opposing inputs yield outputs that are neither equal nor opposites. If they were equal, there's a chance g is even. If they were odd, if they were opposites, there's a chance g is odd. These are not opposites, there's no way g is odd either. So right here, g is neither even nor odd. But a question for you. Let's say I found that g of -1 were also 3. Does that mean that g is an even function? If I show this, do I prove that g is an even function? Well, no. Because what about g of 0? Not g of 0 equals g of 0. What about g of 2? What about g of 3? What about g of 4? A single example like this could not prove that a function is even or odd, but a single counterexample can show that g is neither even nor odd. In a way, examples or counterexamples are more easily used to show that something is not true or that a neither case holds than to prove affirmatively that a function is, say, even or odd. Don't worry too much about this. All right. You can ignore the rest of this section, although it's kind of interesting. For example, an even function times an even function is even. An even function times an odd function is odd. It follows the rules of signed numbers. So for example, you can think of an even function as corresponding to a positive number. You can think of an odd function as corresponding to a negative number. A positive times a negative is a negative. And the proof, well, I talk about various proofs. I talk about a proof here in example 7. The proofs are based on that idea. So we can talk about patterns for products and quotients of even and odd functions. In particular, the reciprocal of an even function is even. The reciprocal of an odd function is odd. We're going to see this in trig. By the way, 1, which is a non-zero constant, this represents an even function. So these are special cases of even divided by even is even divided by odd is odd, because 1 represents an even function. In trig, we're going to say that the reciprocal of the sine function, namely the cosecant function, these are both odd, I should say. These are both odd. Sine and cosecant are both odd. Cosine and secant are both even. We're going to see that in trig. We can also talk about symmetry and equations. For example, the equation x squared plus y squared equals 9, the graph of that is a circle, and you can use various analyses to analyze various symmetries regarding this circle. Symmetries about the y-axis, x-axis, origin, and the line y equals x. Next up, speaking of things that don't pass the VLT, consider x a function of y. Graphs, in these cases, they don't have to pass the VLT, but they do have to pass the what? The HLT. That's next.
All right, that's coming up next. In fact, it's one video for one section. We're going to go through this fast. A benefit of coming to class. 1.8, I kind of overwrote it. The video, if you understand the video, you're good. Questions on 1.7, symmetry, even, odd, neither functions. Any questions? Whoops.
Hi, everyone. All right, what if we have x as a function of y? Equations of the form x equals f of y. This time, our inputs are y coordinates and our outputs are x coordinates. Now, the underlying theory of functions is basically the same. So for example, here, consider the squaring function. If you say f of y equals y squared, that indicates the same function as f of x equals x squared. I could say f of grandma equals grandma squared. In both cases, f represents the squaring function. We assume the domain is all reals. Now here, if you think of f of y equals y squared, remember, we can replace f of y with x this time. Before, we replaced f of x with y. Now we're replacing f of y with x. Function values are now x coordinates. They used to be y coordinates. Okay, well, we can do a point plotting table for x equals y squared. Here's a point plotting table for x equals y squared. But this time, the domain consists of y values, basically. The domain consists of y values, basically. So you input various values for y. Domain is all reals. The input values can still be negative. And then we get corresponding squared values. So the square of 3 is 9. The square of negative 3 is also 9. So far, so good. This is very familiar when it comes to point plotting. But here's the difference. Here's where things change. Remember, the input values are the y coordinates. The output values are the x coordinates. So if the input y equals 3 yields the output x equals 9, the corresponding point is not 3, 9, it's 9, 3. You're still following the order x, y. But remember, y this time is the input, x is the output. Likewise over here, the input negative 3 goes into the y position, the output 9 goes in the x position. When you point plot and connect the dots and extend, you get a parabola opening to the right. Now, remember, the squaring function is an even function. Notice the graph here is not symmetric about the y-axis, it's symmetric about the x-axis. So if you have x as an even function of y, you're going to have symmetry about the x-axis. Now, why didn't we see symmetry about the x-axis so often before? This is one of the few times we've seen symmetry about the x-axis. Well, because notice this graph fails what test? It fails the vertical line test. This graph fails the vertical line test. But that's okay, because we have here x as a function of y. We don't have to have the graph pass the VLT. However, we do need it to pass what? We do need it to pass the HLT, which is the horizontal line test. If you look at these horizontal lines, notice there is no horizontal line that intersects the graph more than once. 1 point, 1 point, 1 point, and so forth. This graph passes the HLT, the horizontal line test. Now, you can actually construct this graphs using, in a way, implicit functions. So what's another way of getting this graph over here? Well, we have x equals y squared. What if we turn it around? Y squared equals x. Apply the square root method, y equals what? If y squared equals x, what could y be? Careful, don't forget, plus or minus the square root of x. Oh, and what happens if on Desmos we graph those guys? Y equals the square root of x. That's in red. How about y equals the opposite of the square root of x? That's in blue. Together, they form the graph of x equals y squared in green. It consists of this red graph over here, this blue graph over here. Together, they form the green parabola opening to the right. All right. The horizontal line test. And then the graph may or may not pass the VLT. Now, as I mentioned before, when you do your point plotting, remember that your domain values are like y coordinates and your range values are like x coordinates. Before, when we had y as a function of x, domain was x, range was y. Now it's switched. Domain is y, range is x. Domain is y, the set of all real numbers. Range is x, the set of non-negative reals. Right. Domain corresponds to the y coordinates we pick up on the graph. Range corresponds to the x coordinates we pick up on the graph. By the way, odd functions still have the property that you have symmetry about the origin. For example, here's x equals y cubed. Solve this for y. What do you get? Y cubed equals x. Y equals the what? Y equals the cube root of x. So in case you're wondering how to graph x equals y cubed, it might help to solve it for y. And you better remember how to graph the cube root function. Y equals the cube root of x. These are equivalent equations. These are equivalent equations. And this indicates, by the way, that the cubing function and the cube root function are inverses. We'll talk about that later. Translations. How do we do shifting? This time, the easy shifts are the horizontal shifts or translations. When we had y as a function of x, it was easier to shift things up and down. That was back when we had y as a function of x, back in section 1.4. But now, in this section, horizontal shifts are easier, and vertical shifts are harder because they involve substitutions and the signs surprise. The things that made horizontal translations harder in 1.4 now make vertical translations harder in 1.8. So for example, Consider the graph of x equals y squared. Let's do this on Desmos. Here's the graph of x equals y squared. This time, what happens if you add 2 to the right side? If you add 2 to the right side, you're increasing the x coordinates by 2. What happens then? You're shifting the graph to the right, because for each value of y, for example, y equals 0 here, the x coordinate increases by 2, in this case from x equals 0 to x equals 2. So for each value of y in the domain, you're increasing the x coordinate by 2 units. You're shifting the graph to the right. How do you shift the graph to the left by 2 units? X equals y squared, all minus 2. So this time, the horizontal shifts are easier. Red to blue for a rightward shift, red to green for a leftward shift. The horizontal shifts are easier. The harder shifts are the vertical shifts because they involve substitutions and the sign surprise. For example, to shift this graph up, you substitute with y minus 2. Let's do that. In red, we have x equals y squared. To shift up, it's x equals, you substitute y with y what? If you shift up, it's not y plus 2, it's y minus 2. That's squared. You shift up from the red graph to the purple graph. Confusing because it involves a substitution and the sign is surprising. The things that make vertical translations hard now made horizontal translations hard back in 1.4. The coordinate shifting method I mentioned before, where you replace x with x minus h and y with y minus k, that still works. Again, that's where you replace x with x minus h to shift horizontally, shift y with y minus k to shift vertically. That still applies. Reflections. Here's the key thing. The graph of x equals y squared is in blue. The graph of x equals the opposite of y squared is in red. That's a reflection about the y-axis. And why is that? In red, we have x equals y squared. X equals the opposite of y squared. Well, for each y value in the domain, look along the y-axis, what's happening? Each x coordinate becomes the opposite value from what you got before. So for example, when y equals 1, we have 1, 1 on the red graph for the original. We have negative 1, 1 for this blue point on the black graph. X equals the opposite of y squared. If x equals 1, if y equals 1, x equals negative 1. So for each y value in the domain, the corresponding x coordinate flips over to its opposite. For reflections about the x-axis, you do a substitution. Substitute y with its opposite, but those are more rare. Here I'm doing it to the square root function. X equals root y. You can skip the rest of the section, skim over it. The gallery, this is interesting, but I wouldn't expect you to know it off the bat. Next up, let's talk about inverse functions.
All right, so any question, whoops.
The gallery, this is interesting, but
Okay, so any questions about x as a function of y? So be able to graph things like x equals y squared, for example, understand basic translations, reflection about the y-axis in particular. Even functions will be symmetric about the x-axis this time. So there are only a few things you need to know from 1.8. This is overwritten, so don't worry about the last part of this. Questions? Because we're going to go to the question about what's the deal with domains and ranges kind of flipping around. Inverse functions next.
I wouldn't expect you to know it off the bat. Next up, let's talk about inverse functions. Hi, everyone. In section 1.9, we're going to talk about one-to-one functions and their inverse functions. Only one-to-one functions have inverse functions. One cool thing about one-to-one functions is that their graphs will pass both the VLT and the HLT. So we really like working with these functions and these graphs. Now, what's this idea of inverses? So, for example, when it comes to addition, the opposites, 3 and -3, are additive inverses of each other because they undo each other. When you add them together, you get 0, the additive identity. Likewise, 3 and its reciprocal, 1/3, are multiplicative inverses because when you multiply them, they undo each other and you get 1, the multiplicative identity. So what's the deal with inverse functions? Inverse functions undo each other. And when you compose them, you get the identity function. That's the idea. A pair of inverse functions have the property that when they are composed in either order, the result is the identity function. So the output is the same as the input. If f has an inverse function, we say that f is invertible. This inverse is unique, and it's denoted by f with a -1 superscript. This is called f inverse. F and f inverse are inverse functions of each other if they are invertible. Now, be careful, because remember, x to the -1 means 1 over x. Here, x is a variable. But when you see a function like f with a -1 superscript, this generally does not mean 1 over f. This does not mean reciprocal. It means function inverse.
So it's not an exponent. -1 is not an exponent.
When I said earlier that they compose to the identity function in either order, what I mean is that if you take an input x, you apply the f function, and then you apply the inverse function. So it's like you plug a number into a calculator in the domain of the inside function f. If you press the f button, take the result, press the f inverse button, you're going to get x back. Likewise, if you take x, if it's in the domain of the inside function here, f inverse, if you take this value, apply f inverse, press that button, take the result, press the f button, then again, you're going to get x back. In that sense, f and f inverse undo each other. Some pictures will help. Let's look at example 1 on temperature conversion. Let's say that f is the function that converts temperature measures from the Celsius scale to the Fahrenheit scale. That's what the function little f does. The function little f, inverse, will then convert from Fahrenheit back to Celsius. It's going to undo what the f function does. So for example, consider these diagrams over here. Consider the freezing point of water at sea level. Bear in mind that the freezing point varies with elevation, but at sea level, the freezing point of water is given by 0 degrees Celsius. But it's also given by 32 degrees Fahrenheit. This f function that converts from Celsius to Fahrenheit would take you from 0 degrees Celsius to 32 degrees Fahrenheit. Likewise, if you consider the boiling point of water at sea level, the f function takes you from 100 degrees Celsius to 212 degrees Fahrenheit. I think in Denver, the boiling point of water is more like 202 degrees Fahrenheit. So this is all at sea level. But now what does f inverse do? F inverse is going to convert from Fahrenheit back to Celsius. So f inverse takes you from 32 degrees Fahrenheit back to 0 degrees Celsius. And f inverse here takes you from 212 degrees Fahrenheit back to 100 degrees Celsius. F inverse undoes what f does. So take a look at this input-output table. The F function converts from Celsius to Fahrenheit. 0 goes to 32. But F inverse goes from Fahrenheit back to Celsius. Fahrenheit back to Celsius. 32 goes to 0. So the input here becomes the output here. And the output here becomes the input here. In that sense, F and F inverse switch inputs and outputs. Now, what happens if we start with 0 degrees Celsius? Let's start at the beginning. We start with 0 degrees Celsius. I'll do this in green. 0 degrees Celsius. We apply the F function, which converts you from 0 degrees Celsius to 32 degrees Fahrenheit. And then what's F inverse of 32? What happens if we apply the F inverse function? We go from 32 degrees Fahrenheit back to 0 degrees Celsius. So the input at the beginning was 0. The output at the end is 0 degrees Celsius. The input becomes the final output. That's why I meant up here when I said that when you compose the functions in either order, a function and its inverse, the composition is the identity function because the output is really the input. So you can start anywhere. If you do the loop-to-loop, right, whether you apply F first and F inverse, or if you apply if you apply F inverse first and then F, it doesn't matter which order you apply them to. As long as the inner number is in the domain of the inside function, you're going to get that number as your final output. I'll do this quickly with 32. If you start at 32, apply F inverse, you go to 0. What's F of 0? You get 32. You do a loop-to-loop. The final output was the input. Right. This idea of switching inputs and outputs is a key theme. If F has an inverse function, F inverse, then F of A equals B, F maps A to B, if and only if F inverse maps B back to A. F of A equals B if and only if F inverse of B equals A. We switch inputs and outputs when you go from a function to its inverse. So if you switch sets of inputs and sets of outputs, that means that the domain of a function that's invertible will equal the range of the inverse function. Bottom line, if you have an invertible function and its inverse function, their domains and the ranges will switch. The domain of one becomes the range of the other. They switch domains and range because they switch sets of inputs and outputs. Now, what kinds of functions have inverse functions?
Right. Any questions so far? Any questions so far? The idea of F and F inverse undoing each other. And you know what? It's a good time to do a video. A little fun video. I think it's about time. There's been a lot of theory so far. So let's do this. Definitely watch it. Yeah.
Hi, everyone. What functions are invertible? What functions have inverse functions? One-to-one functions. These are functions whose graphs will pass both the VLT, because they're functions, and also the HLT, because they're one-to-one functions. We love these kinds of functions. So for example, here's a one-to-one function, the cubing function. Well, how do you graph y equals x cubed? Is that rising snake. The cubing function is a function. The graph passes the VLT, but Because it's a one-to-one function, it also passes the HLT, the horizontal line test. So because of that, it's a one-to-one function. That means it has an inverse function. And what is its inverse function? What undoes taking the cube of something? Taking its cube root. F inverse of x would be the cube root of x. The domain and range would be R in both cases. So for example, F takes in 2, takes the cube of 2, the result is 8. F inverse takes in 8, takes the cube root of 8, and gets back 2. It's a perfect loop-to-loop. And this is true for any real number, here or here. You get a good loop-to-loop. Now, the cubing function and the cube root function, which by the way is this guy over here, y equals x to the 1/3. In blue, that's the cube root function. That also passes the VLT and the HLT. These are both one-to-one and invertible functions. Now, notice here I started with the cubing function and the cube root function. What about squaring and taking a square root? Again, believe it or not, the odd cases are much easier than the even cases. We're going to talk about the squaring function next time. The squaring function is not one-to-one.
All right, think about the problems with the squaring function. What's different about y equals x squared from y equals x cubed? Why do we have more of a problem with y equals x squared? Any questions about the cubing function and why it's one-to-one? Passes the VLT, passes the HLT. Graph passes both tests. Nice loop-to-loop. All right.
Hi, everyone. What does the cubing function have that the squaring function doesn't? The cubing function is one-to-one. So, for example, consider the graph of y equals x cubed. Let's say I have a point on this graph and you care. And let's say I tell you that my point has x coordinate 2. You know that the y coordinate has to be the cube of 2, or 8, because we have a function. If I give you x equals 2, you know y equals 8. But wait a minute. Let's start at the beginning. Let's say I tell you that my point has y coordinate 8. You know that the x coordinate has to be 2. If I tell you that the y coordinate is 8, you know that the x coordinate has to be 2, because this cubing function is a one-to-one function. The squaring function does not have that luxury. What was the problem with the squaring function? If you graph y equals x squared, the problem is that the graph, this parabola, will fail the horizontal line test, the HLT. Because, for example, the point 3, 9 lies on the graph, and the point -3, 9 lies on the graph. And the line y equals 9 will pass through both points, that horizontal line. So what this means is that we have two competing values for x here. The square of -3 is 9, but the square of 3 is also 9. We have Jennifer and Angelina competing for Brad. We have two numbers here, two different x coordinates, whose square gives us the same y coordinate, 9. And that's reflected in the fact that the graph here fails the HLT. The point -3, 9 lies on the graph. Also the point 3, 9 lies on the graph. Here's a graph of y equals x squared. Let's say I have a point on this graph and you care. Now here's the problem. If I tell you that my point has y coordinate 9, unlike for the cubing graph, you're not sure what the x coordinate is, because I could be talking about the point 3, 9, or I could be talking about the point -3, 9. You don't know which point I have. We don't have a clean loop-to-loop here. If I tell you my y coordinate's 9, you don't know where to go back. This function is not invertible. If I tell you the y-coordinate of my point is 9, you don't know what the x-coordinate is. Basically, 9 has two square roots, positive 3 and negative 3. Who does Brad go back to? It's not a clean loop-de-loop. The way we had for the cubing and cube root functions. We had a clean loop-de-loop. There was no competition. Here, we have competition. Brad could go back to Jennifer or Angelina. So if we try to invert this function, we cannot get an inverse function because an inverse function cannot do something like this. Because no function will allow one input to yield two or more different outputs. So that's the problem. As it stands, the squaring function on the reals does not have an inverse function. You cannot reverse these arrows so that we get an inverse function. Well, question, how can we get an invertible version of this? And then how can we get the square root function? Now we're going to do this in trig as well. We're going to restrict the domain. It's true that this parabola, y equals x squared, fails the HLT. But do you see a piece of this parabola with the same range? It's as tall as the original graph here, but that will pass the HLT. Do you see a piece of this parabola that will pass not just the VLT, but the HLT? And it's as tall as the original graph. Don't just grab one point. No fair. Yes. By convention, we grab the right half of the parabola, the right half. You'll see that the range is the non-negative reals, just like before. It's as tall as the original graph in that sense. But this time, the graph passes the HLT. So the squaring function, if it's restricted to this domain, the non-negative reals, is also the range, then it turns out that this function will be invertible. I call this new function g because technically, if you change the domain, you change the function, even though the rule, x squared, is still the same. But now we have an invertible one-to-one function. So 3, we know, goes to 9, and 9 has to go back to 3. It has to go back to Angelina. Negative 3 has nothing to do with anything. So now we have a nice loop-to-loop. All right. So a function is one-to-one if and only if the graph in the xy plane passes the HLT as well as the VLT. Remember, this restricted graph here on the restricted domain passes not just the VLT, but also the HLT. And again, because it's a one-to-one function now, it has an inverse. Namely, g inverse of x is going to be the square root of x. G inverse is the square root function. The square of 3 is 9. Now, the principal square root of 9 is 3, only positive 3. The inverse is a function. Next, how do we graph inverse functions?
Any questions? Any questions? It's 8:15. I think it's a good time for a break. I'll see you at 8:26. All right. All right. Until 8:26. Don't forget to mute. I have to remember to record. All right. All right. Graphing inverse functions next.
Hi, everyone. How do you graph inverse functions? It comes down to the theme of switching inputs and outputs. Let's go to our previous example. Let g of x equal x squared on the restricted domain, the non-negative reals. So for example, g of 3 equals, well, what's the square of 3? It's 9. So we can say then, g of 3 equals 9, and therefore, when graphing y equals g of x, the point 3, 9 appears on the graph. Because the input x equals 3, the output y equals 9. But now, what does the g inverse function do? It takes the principal square root. G inverse of 9 is, well, what's the principal square root of 9? It's 3. Do this in blue. G inverse of 9 is 3. The principal square root of 9 is 3. So, if you consider the graph of y equals g inverse of x, if you consider the graph of y equals g inverse of x, what point lies on the graph? What point lies on the graph? The point 9, 3. Because this time, if the input x equals 9 for the g inverse function, the output y equals 3 for the g inverse function. So notice that 3, 9 lies on the original graph, 9, 3 lies on the new inverse graph. That corresponds to the fact that the point 3, 9 lies on the graph for g here, and the point 9, 3 lies on the graph here for g inverse, the square root function. Again, g takes you from 3 to 9, g inverse takes you from 9 to 3. On the original graph for g, the point 3, 9 appears on the graph. On the new graph for g inverse, 9, 3 appears on the graph. In general, if f is invertible, the point AB lies on the graph of y equals f of x, if and only if the point BA lies on the graph of y equals f inverse of x. You switch inputs and outputs. If 3, 9 lies on one graph, 9, 3 lies on the other, and so on. 2, 4 goes to 4, 2, and so on. AB goes to BA. AB goes to BA. Just like 3, 9 goes to 9, 3. In that sense, you can do point plotting and you can graph the inverse graph. The graph of a function, a one-to-one function, and its inverse function, these graphs will be symmetric about the line y equals x. To get from one graph to the other, you reflect the graph about the line y equals x to get the other graph. All right, next up, if I give you a formula for f of x, how can you find a formula for f inverse of x?
Do you remember how to do that from your algebra class? That might ring some bells. Any questions? Any questions? Graphically, the key thing for inverse functions, AB goes to BA.
Hi, everyone. If I give you a function rule, f of x equals ... and it's a one-to-one function, how can you find a rule for f inverse of x? We'll start by using a conceptual approach, and then we'll show a mechanical approach later on, the one you're used to from your Algebra 2 class. Now, for the conceptual approach, understand that f inverse has to undo the process applied by f. I have a question for you. I'm going to take you way back. When you dress, you put on your socks, and then you put on your shoes. Think Mr. Rogers. Now, when you take off your shoes and your socks, what do you do first? Do you rip off your sock? No. You take off your shoes, then you take off your socks. Think Mr. Rogers. I'm not kidding. So what's the point I'm making here? To determine F inverse, we need to invert or undo the steps, taking off your socks, taking off your shoes, but in reverse order. Because even though you put on your socks first, you have to take off your socks last. All right. And then also, if necessary, impose restrictions to make sure the domain of one is the range of the other for F and F inverse. We'll talk about that with temperatures later on. All right. So let f of x equal the fraction, the cube root of x plus 5 all over 7 on the reals. Find f inverse of x. Okay, so we start with the input x. What does f do to x? Tell me the 3 things in order that you do to x and then the resulting outputs. First, you do what? First, you take the cube root of x. So you take the cube root of the input. And then what do you do to the result? So we now have the cube root of x. What do you now do with the result? You add 5. You add 5 to the result. And then what do you do to this numerator? You divide it by 7. So you can think of the function as applying a 3-step process. It takes in the first input x, applies the cube root, takes the result, adds 5, takes the result, divides by 7. Now what is f inverse going to do? F inverse is going to undo these things. So what undoes taking the cube root of something? Taking the cube of something. What undoes adding 5? Subtracting 5. What undoes dividing by 7? Multiplying by 7. But remember the shoes and socks example. These steps have to be done in reverse order. So it's kind of like here, you're taking off your shoes first when you multiply by 7. So what does f inverse do to its input? You first multiply by 7. Then you take the result, subtract 5. Then you take the result and cube. So what do? We start with x. We multiply by 7. Take the result, subtract 5. Take the result, cube it. And that's our rule for f inverse of x, right here. We take x, multiply by 7, take the result, subtract 5, take the result, cube it. The domain and range for both functions is all reals. All right. Now, in your Algebra 2 class, you may have applied the mechanical approach, which is fine. We'll do it along the way. All right. So again, let f of x be this rule over here. What do? We start by replacing f of x with what letter? Y. Replace f of x with y. Right? And then what was the key theme for inverse functions? We switch inputs and outputs. Switch x and y. So we now have x equals the cube root of y plus 5 all over 7. Now you solve for the new y. And think about the steps you apply. What do you do when you solve for y? What do you do with the 7? You multiply it on both sides. Then what do you do with the 5? You subtract it off of both sides. Sounds familiar? Then you do what? You take the cube of both sides. Sound familiar? That's what we did in the conceptual approach. Multiply by 7, subtract 5, cube the result. Multiply by 7, multiply by 7, subtract 5, cube the result. All right. Switch sides, y equals the cube of 7x minus 5. Right? And note that we're finding a rule for f inverse. F inverse of x is the cube of 7x minus 5. Same as what we got from before. All right. If necessary, impose restrictions to make sure these happen. Don't worry about that, but I'll discuss a temperature application in a moment.
Okay, any questions? Any questions? By the way, while we're at the shoes and socks example, I couldn't resist. All right. So we did the mechanical approach. Now we're looking at graphs, right? All right, we're looking at graphs. Oh, everyone loves Mr. Rogers. Who didn't? Watch the documentaries on him. Great documentaries. All right. Whoa, wait a minute. One moment. There we go.
Everyone, let's verify our inverse function rule graphically. Let's start by graphing the original function, y equals the cube root of x plus 5 all over 7. Y equals, parenthesis, the cube root of x, that's x to 1/3, 5 all over 7. That's the original graph of the function. My proposed inverse function is given by the cube of 7x minus 5. Y equals 7x minus 5 all cubed. The red graph and the blue graph better be reflections about the line y equals x. And yes, they are. For example, the y-intercept here is the x-intercept over here. Notice that both the red graph and the blue graph pass both the HLT and the VLT. These are both one-to-one functions. All right. Oh, and by the way, let's look at y equals x cubed, the tall proud snake. The inverse graph, y equals the cube root of x. Oops. X to the 1/3.
That's a lazy snake.
I claim that the red graph and the blue graph, sorry, the red graph and the green graph are inverse graphs. The line of reflection is y equals x, that purple line. And yes, the red graph and the green graph are reflections of each other about that purple line, y equals x. Looks like a DNA strand. With temperatures, so it turns out that this linear function converts from Celsius degrees to Fahrenheit degrees. Now you're going to show in the homework that the inverse function that takes you from Fahrenheit to Celsius is given by this rule. Now, when you graph the two functions, f and f inverse, f converts you from Celsius to Fahrenheit. For example, 0 goes to 32. F inverse converts you from Fahrenheit to Celsius. For example, 32 goes to 0. In fact, there's a table, rapidtables.com, that's a website. Okay, 0 degrees Celsius converts to 32 degrees Fahrenheit. Also, there's a Fahrenheit to Celsius page. 32 degrees Fahrenheit converts to 0 degrees Celsius. You see formulas in here. Now, this idea of restricting domains and ranges, now, there is a coldest temperature. It's called what? It's called absolute zero, or 0 Kelvin. In fact, you could argue that I should have open endpoints here. Although some physicists believe that absolute cold is the same as absolute heat. Go figure. But sometimes you have to restrict domains and ranges.
By the way, while we're at it, there was something I just remembered I needed to pull up. Let me see if I can pull it up here. Let me see if I can pull it up. Yeah, here it is. I know a chemistry professor, Fremlin, probably likes this. If you know physics, that's funny. 0 Kelvin is very cold. He's okay, 0 Kelvin, whatever. All right.
Again, these two graphs are reflections about the line y equals x, this slanted line. Oh, and this is an interesting point over here. The intersection point between the two graphs. that is the point, and it's on the line y equals x, that's the point -40, comma -40. What's the significance of that? -40 degrees Fahrenheit is -40 degrees Celsius, and vice versa. So it's the one number for which, if you say, brr, it's -40, it doesn't matter if it's Fahrenheit or Celsius degrees. It's the same temperature. Very cold. That's it.
All right. Any questions about inverse functions? 1.10 and 1.11 are just different applications, so we're kind of getting away. These are applications for calculus. Any questions? Any questions? We're kind of moving away from inverse functions. Any questions? All right.
Hi, everyone. More fun with functions. In section 1.10, we're going to talk about difference quotients, which relate to average rates of change. These ideas will relate directly to section 1.11 on derivatives, which is a key topic in calculus. So what is an example of a difference quotient? Well, the most common geometric application is that it's the slope of a secant line. So let's say that you have a function f. We have here the graph of y equals f of x. It's a nice graph, no weird jumps or breaks or anything. Take two distinct points on the graph, a comma f of a and b comma f of b. Remember, function values correspond to y coordinates. Connect the dots. The line that connects these 2 points is called a secant line. And the slope of this secant line has an important application. The slope of the secant line gives the average rate of change of the function f on this interval from x equals a to x equals b. Assume for now that b is greater than a. Average rate of change is given by the slope. What slope? Rise over run. The rise is f of b minus f of a. The run is b minus a. In principle, b could even be less than a in this formula. B could be here, a could be there. Rise over run. Now look what we have here. Why is this called a difference quotient? Because it's a quotient of differences. On the top, we have a difference of outputs. On the bottom, we have a difference of inputs. Change in y over change in x. Change in outputs over change in inputs. A difference quotient. A common application of difference quotients is average velocity. Average velocity is perhaps the most important example of an average rate of change. So for example, let's say you're in the movie Speed. You're Keanu Reeves or Sandra Bullock. And the villain, Dennis Hopper, says, okay, hotshot, here's the deal. Wherever you are, we're going to call that the 0 milestone. You're at position 0, at time t equals 0. Let's say noon. Now here's your task. You must travel 100 miles due north in exactly 2 hours. So exactly 100 miles in exactly 2 hours. If that's the case, what does your average velocity have to be in order to accomplish this task? All right. Average velocity on this time interval is given by change in position over change in time. Position is often denoted by s. Change in position, delta s, over change in time, delta t. And by the way, it's change in position over change in time. There's a high school teacher in North Carolina who was angry at physics textbooks for saying position over time. No, it's change in position over change in time. Because we don't care if this is happening in California or New York or Utah. What matters is the change in position. And it doesn't matter if it's happening on a Sunday, a Monday, a Tuesday, or for that matter, if you're starting at noon or at 1 p.m. or 2 p.m. What matters is the change in time. The average velocity is given by the change in position over the change in time. The change in position is given by S of B minus S of A, S of A. Your position at the end time minus your position at the beginning time over the change in time, B minus A. So here, the average velocity from noon to 2 p.m., your position at 2 p.m. is at the 100 milestone, the 100-mile milestone, minus your position at time 0, noon, is the 0 milestone, all over 2 minus 0, that's 2 hours. From noon to 2 p.m., the change in time is 2 hours. So the difference quotient here is given by 50, and the unit is given by basically the y unit over the x unit. Here, it's the s unit over the t unit. The unit of position over the unit of time. Unit of position is miles, unit of time is hours, so it's 50 miles per hour, or 50 mph. Remember, the unit is given by the top variable's unit over the bottom variable's unit. All right, 50 miles per hour. It makes sense. In order to travel 100 miles due north in exactly 2 hours, your average velocity must be 50 miles per hour. So what are some strategies? Well, assuming that you have a clear road that's going due north, you can go steadily, 50 miles per hour, go at a constant velocity. Or maybe you start off slowly and then you realize, uh-oh, I better speed up near the end, so I hit that 100 milestone at 2 p.m. Or maybe you panic, you start off going really fast, you might even overshoot and then go backwards. Over here, the velocity would be negative, by the way. Still, the average velocity would be 50 miles per hour. It's the slope of the secant line between the point 0, 0 and the point 2, 100. Remember, at time 2 p.m., you better be 100 miles due north of the starting point. Now, there's a theorem in calculus called the mean value theorem for derivatives. So here's the idea. Let's say that Dennis tells you, all right, hotshot, here's the problem. As you're accomplishing this task, there's a bomb on the bus. The bomb will go off if the bus ever hits exactly 50 miles per hour as instantaneous velocity. So if the bus ever hits 50 miles per hour on that speedometer, the bomb will go off. How should you feel? Very badly. Because unless there's a gap in the road or something, and there is in the movie, but unless there's a gap in the road or something, yeah, if the average velocity is 50 miles per hour, and if there are no gaps or anything, then at some time in here, at some time point in here, the instantaneous velocity will have to match the average velocity. In other words, your speedometer will have to hit 50 miles per hour at some time in here if you're going to have an average velocity of 50 miles per hour. Graphically speaking, at some time in here, the tangent line, this line that models the graph locally, the tangent line must be parallel to the secant line. They must have the same slope. Here, the instantaneous velocity is 50 miles per hour. That's the slope of the tangent line. Here, the slope of the secant line is the average velocity, 50 miles per hour. If these slopes match, the bomb will go off, you're in trouble. That's from the mean value theorem for derivatives. Next, what are some forms for difference quotients and how do we evaluate or simplify them?
All right, folks, you know what's coming next. Let's do it. All right.
Hi, everyone. So let's now talk about different forms of difference quotients. So the first form I discussed involved fixed values for A and B, and therefore fixed function values. Well, the form of the difference quotient is the slope of the secant line, rise over run, f of b minus f of a all over b minus a. You should know that. This is the average rate of change of f on this interval. I'll skip the next two forms. I'll go straight to form 4. This is where the x-coordinate here might vary, and the run, h, might also vary. So here, it's like we have a point with x-coordinate x rather generically, another point here with x-coordinate x plus h. The run here is h. In fact, h could be negative. The point could be over here to the left of this point. Again, the slope of the secant line is given by rise over run. So f of x plus h minus f of x all over h, the run here. We'll see this when we develop the limit definition of derivatives in the next section. Now, let's apply the first form. A company sells widgets, a fictional object. Assume that all widgets produced are sold. Maybe a widget is a gallon of ice cream. Let P be the profit function for the company. P of X is the profit in dollars if X widgets are produced and sold. So our profit model looks like this. P of X equals the opposite of X squared plus 200X minus 5,000 in dollars. Find the average rate of change of profit between 60 and 90 widgets. So if we increase our production from 60 widgets to 90 widgets, what is our average rate of change of profit? We're going to treat the domain of P as the non-negative reals. So maybe it's appropriate that widgets are like gallons of ice cream. You can have non-integer values like 3.5. These aren't like cars. Okay. So we want to know the average rate of change if we go from 60 to 90. Well, it's going to be similar to form number 1 here, except that instead of the f function, we have the p function. We know that we're going from 60 widgets, a equals 60, to 90 widgets, b equals 90. So on the top, we have p of 90 minus p of 60 over 90 minus 60. We want to simplify this. This is the average rate of change of profit going from 60 widgets to 90 widgets. Well, here's the formula for P of X. P of 90, plug in X equals 90. P of 60, plug in for P of 60, plug in X equals 60. You might want to work these out separately. Here it's one big formula here. And also don't forget the grouping symbols. If you don't work these out separately, then definitely put grouping symbols around the second group. They're not as necessary in the first group. Divided by 90 minus 60 is 30. All right. So work it out and we get, now P of 90 minus P of 60, this numerator, P of 90 minus P of 60, the change in profit is $1,500, going from 60 widgets to 90 widgets. We're dividing by the 30 widgets, the run. So the difference quotient is $50 per widget. Remember, it's dollars of profit over widgets. It's the P unit over the X unit, basically. Dollars per widget, $50 per widget. So again, the practical interpretation is that if the company increases its production from 90 widgets to from 60 widgets to 90 widgets, then its profit will increase by a rate of $50 per widget on average. The total increase in profit is $1,500 and is spread out over the 30 additional widgets when you do the average rate of change. Again, the difference quotient gives the slope of this orange secant line. Rise, the total change in profit, over run, the increase in the production level. $1,500 per widget. That's the slope of this orange secant line.
Oh, well, $50 per widget.
The fact that the slope is positive, it's an upward sloping line, reflects the fact that the profit function is increasing in that vicinity. Over here, the average rate of change of profit would be negative. And up here, it'd be more of a wash. We're going to skip the next two examples. Let's go straight to example 5. Again, same profit function. P of x equals the opposite of x squared plus 200x minus 5,000. Evaluate and simplify this expression. The difference quotient, P of x plus h minus P of x all over h. Two tricky things here. For P of x plus h, how do you write that out? Hint, it involves what? S word. Substitution. You're going to substitute x plus h in parentheses into x here and here and here. Also over here, when you plug this in for P of x, you're going to need something. You're going to need grouping symbols. All right, so this is a big first step here. Many students, if they can make it to here, they're set. So P of x plus h, we're going to do a bunch of substitutions. The opposite of, instead of x squared, is the opposite of the square of x plus h. Plus 200 times, instead of x, it's the quantity x plus h. Minus 5,000, nothing changes there. Minus, again, don't forget the grouping symbols, because you're subtracting something with more than one term. And we just have the P of x rule. The opposite of x squared plus 200x minus 5,000. All that goes over h. Rise over run. If you get this, you're set. Now, it helps to square this binomial. The opposite of the square of x plus h is not just x squared plus h squared. It's x squared plus 2xh plus h squared. Don't miss this middle term. So after this step over here, a key error to avoid is that you need to remember to not miss the middle, the 2xh term. Plus, here I'm distributing, we can wait, 200x plus 200h minus 5,000. Minus, in brackets, again, copying P of x. All that over h. Then I distribute the -1 through here, the opposite of x squared, minus 2xh, minus h squared. If you haven't distributed yet, distribute, plus 200x, plus 200h, minus 5,000, minus, again, don't forget the grouping symbols, or distribute the -1 right now. Do one or the other. All over h. Now, when I distribute the -1 here, what ultimately happens on the top? It's a massacre. So we get the opposite of x squared minus 2xh minus h squared plus 200x plus 200h minus 5,000. Then we flip all these signs here. Plus x squared minus 200x plus 5,000. And we get a bunch of cancellations. The opposite of x squared and the x squared, they add up to 0. That's a cancellation. 200x minus 200x, that gives 0. And negative 5,000 plus 5,000, that gives 0. There are only 3 terms that survive on top. Write them out. Make sure you put this as a separate step. Don't combine too many steps at once. What survives on top? Negative 2xh minus h squared plus 200h, all over h. Now, what can we do on the top? We can factor out what? We can factor out the h. H times the quantity, when you factor, you divide. Negative 2x minus h squared divided by h is h, plus 200h divided by h is 200, all over h. H divided by h is 1, provided h is not 0. That's a hidden restriction here. So finally we get the opposite, negative 2x minus h plus 200, provided h is not 0. So we don't want h to be 0, but when we do derivatives in the next section, we're going to let h approach 0. So whatever x and h are, this here is a formula for the slope of the secant line. But this is a very handy-dandy formula, because remember the earlier example. in the earlier example, we asked, what was the average rate of change of profit if production went from 60 widgets to 90 widgets? Well, we can now use the handy-dandy formula. We don't have to work a difference quotient out. We already have a handy-dandy formula. Negative 2 times, we start at 60 widgets. That's the starting point. We start with x equals 60. Now, if we're increasing production from 60 widgets to 90 widgets, what's the run? 90 minus 60 is 30 widgets. That was the denominator in our earlier example, 30 widgets. Minus, again, h is 30. That's the run, plus 200. And this turns out to be, guess what? 50. The unit for y, or profit, is dollars. The unit for x is widgets, $50 per widget. $50 per widget. And that was the average rate of change we found back here when we just plugged in numbers. Up here, we found the average rate of change of profit between 60 widgets and 90 widgets. Okay. Instead of having to go through all this, we have the handy-dandy formula, and we got the same result, $50 per widget. Although, of course, we did use a difference quotient, and we simplified it in order to get this formula in the first place. But now that we have this formula, you can quickly answer questions like, okay, so what's the average rate of change of profit if we go from 100 widgets to 200 widgets? Well, we do right now. Negative 2 times x is 100 minus the run h is also 100 if you go from 100 to 200 widgets, plus 200. All right. Negative 200 minus 100, that's negative 300, plus 100, we get negative $100 per widget. Which makes sense because by the time you're out to 100 to 200 widgets, you're out here. And we know that the profit function is sloping downward. So it's negative. Our profit is decreasing. All right, handy-dandy formula. Next, what happens if h approaches 0? We get what's called the derivative, which is a keystone of calculus.
Oh, yes. All right. Now, before I go on, I have to do something with widgets. A good comedy from the 1980s called, what is it? All right, derivatives. Now, folks, derivatives is optional. You don't have to know 1.11, but bottom line, you're letting h approach 0. If you look at the optional homework, it's actually very easy. The hard part was 1.10. 1.11 is easy. But 1.11, although it's optional, this is the gateway to calculus. I encourage you to stick around. Introduction to derivatives, okay? Let's look at it.
Hi, everyone. Section 1.11 is an optional introduction to derivatives in calculus. Now remember, when we were talking about slopes of secant lines and average rates of change, we looked at this difference quotient, rise over run. F of B minus F of A all over B minus A, rise over run. Now let's say that instead of the constant B, let's consider the variable X. We'll let X change, but we'll let A stay fixed. So we have a variable right endpoint over here. Now let's say that I want to know the instantaneous rate of change at A. That's going to be the slope of this tangent line. And that's going to be the derivative, the slope of this tangent line. So how do we get the slope of that tangent line? We go through this limiting process. So at x equals A, consider the corresponding point A f of A. And then consider this sequence of second points along the graph as the x-coordinate moves towards the a-coordinate, either from the right or from the left. Consider the sequence of secant lines. Each secant line has a slope. And the idea is that as x approaches a, we often do use arrows in calculus, as x approaches a, the slopes of the secant lines will approach the slope of the tangent line. Slopes of secant lines will approach the slope of the tangent line here. And the slope of the tangent line is called the derivative. The derivative of f at a. Which is often denoted by f prime of a. The derivative of f at a, that's the slope of the tangent line at x equals a. The slope of the tangent line that touches the graph at this point. And the idea is that this tangent line is going to be the best linear approximation to this graph near this point. F prime of a, the derivative of f at a, is the slope of the tangent line to the graph of f at the point a f of a, if that slope exists. If we get a vertical tangent line, the derivative does not exist. Sometimes, like for absolute value, there's a mismatch of slopes. There's no derivative at x equals 0. If f prime of a exists, we say that f is differentiable at a. There is a single tangent line, and it's not vertical. Like over here, we have a single tangent line, it's not vertical, and it works from both sides, from the right and from the left. So here's one way to define a derivative. You take this difference quotient, rise over run, f of x minus f of a, all over x minus a. Let's say this is the x-coordinate here. We take the limit as x approaches a. So this is the slope of the secant line. We want to know what the slopes approach as x approaches a. Another way to look at this, going all the way down here. We've seen this before, rise over run, where this is really focusing on the run. The rise is f of x plus h minus f of x. The run is just h. Rise over run. And we take the limit as h approaches what? To get the slope of the tangent line. We take the limit as h approaches 0. So h values can be positive, h values can be negative, but either way, they're approaching 0. The run. F prime of x, the derivative at x in general, is the limit of this difference quotient as h approaches 0. This is the limit definition of the derivative. It's perhaps the most famous form. And you can think of the derivative function as a slope function. For example, here's y equals x squared. The derivative function is given by y equals 2x. So the value of 2x, the y-coordinate on the green graph, gives the slope of the tangent line to the red graph. At x equals 0, 2x equals 0, the y-coordinate on the green graph is 0, so there's a horizontal tangent line for the red graph. When x equals 1, 2 times 1 is 2. That's on the green graph. The point 1, 2 is on the green graph. The slope of the tangent line at x equals 1 on the parabola here is 2. So again, the y-coordinate on the green graph gives the slope along the parabola. The y-coordinate, the 2x value, gives the slope for the graph of y equals x squared.
Any questions? Derivatives are slopes of tangent lines. Derivative functions are slope functions. They describe how the thing curves, how the slopes change, right? So the slopes are negative over here. That's why you have the green below the x-axis. The slope is 0 at 0. The slope is positive here. That's why the green piece is above the x-axis.
The instantaneous rate of change of f at a is equal to the derivative, f prime of a, if it exists. So an example is velocity, like instantaneous velocity of a car. Imagine this. Let's say that we want the instantaneous velocity at time 1 p.m. Consider the average velocity between 1 p.m. and 2 p.m. Basically, let's say it's 1 p.m. right now. I want to know the average velocity of the car in the next hour. Let's say it's 7 miles per hour. I'm driving in a parking lot. Then consider the average velocity in the next minute from 1 p.m. to 1:01 p.m. The average velocity over the next second, over the next millisecond, over the next microsecond, and so forth. You're approaching, the average velocities here are approaching the instantaneous velocity at 1 p.m. How can you find a derivative? Remember that profit function we had earlier for the widgets? The difference quotient simplified to this. That was the slope of the secant line given the starting value x and given the run h. This gave you the slope of the secant line, the average rate of change. What happens as h approaches 0? We plug in 0 for h and we get this. Negative 2x plus 200. That is a derivative function rule. Just as the derivative of x squared is 2x. Likewise, the derivative of that profit function we had, way up here, the derivative of this profit function is given by p prime of x equals negative 2x plus 200. That's a slope function. If you plug in x equals 60, we get $80 per widget. That's the instantaneous rate of change at 60 widgets. So at 60 widgets, the slope of the tangent line, the derivative, is $80 per widget. That's the slope here. Which means that if we're going from 60 widgets to 61 widgets, that means that our profit is increasing by about $80. That was the idea of slope as marginal change. We saw that in 0.14. Well, if you know slopes and points, you can get equations for tangent lines. And there's a principle called local linearity. The idea that if we take a graph, like for example, the graph of y equals the square root of x. If you take a point on the graph, like say 1, 1, zoom in really close, and more, the graph looks like a what? Looks like a line. Anytime you have differentiability, if you zoom in really close on the point, the graph's going to look more and more like a line. And you can use linear approximations to approximate the function value for values of x close to 1 here. The tangent line is basically the graph. The tangent line does a really good job of approximating the graph near the point of tangency. Remember, the tangent line only has to go through one point on the graph. So even though we normally talk about two distinct points determining a line, a tangent line only has to go through one point on the graph. But it's a limiting process. We let the second point approach the first point. Secant lines approach the tangent line. Again, if the run is 1, the rise is the slope. The derivative is an approximation. So for example, if we produce one more widget, the profit increases by about $80, the derivative. The derivative was $80 per widget. P prime of 60 was $80 per widget. Graphing. If you have a derivative function, hey, if you know where the derivative is positive, if you know where the derivative is negative, if you know where the derivative is, what's the slope of this tangent line? 0, that can help you graph functions. And we're especially interested in max points and min points. Max points and min points. And that's where the derivative is either 0 or undefined. For absolute value, at this point here, the derivative is undefined. All right, that was a preview of derivatives. You're going to use them to graph functions and much more. To find out where you can get local max or min points, you set the derivative equal to 0 or see where it's undefined. In calculus, you'll learn much more about derivatives.
All right, well, that's that. That's chapter 1. All right. Remarkably, I finished kind of early today. That's unusual for me. All right, so it's 9:20. It's 9:20. Are there any questions? You're going to jam on that homework this weekend, right? I have to grade. I mean, like I said, this month is going to be slow grading. Okay, then in October, I'm really going to be freed up when those videos cycle around. All right, but any questions? That's chapter 1. I will stick around for additional questions you may have. We're still recording. Any questions while we're still recording? Otherwise, well, any questions while we're still recording? You don't mind sharing with the class? Any questions? Any questions? Sure. Yeah. Okay. So, and you're okay. Yeah. So, yeah, we can keep. So I'm recording. Of course, feel free to go. I'm recording, and if you want me to stop recording, let me know. All right. All right. Let's see here. 141 homework is here. All right. Okay. Yes, you're all welcome. Yeah, take care. Have a great weekend. Okay. Again, I'm still recording now. If you want me to stop the recording, let me know. All right. So first two of 1.3. Oh, this is 0. Let me get 1. I'll just get to the yeah. I'll just get the homework. It's 1B now, right? Okay, 1B. Time flies. All right, here we go. All right. First two on 1.3. Okay. Oh, yeah, right. The even odd issues. And in fact, we talked about some of the principles today. So I guess your knowledge of 1.7 might help here now, right? Okay. Is f even, odd, or neither? This is not a polynomial, all right? So this is what might help. And I know it's hard to chat this, but how can you rewrite this as a radical? How can you rewrite x to the 4/5 as a radical? Well, we can put x to the 4th on the inside, for example, and we take the 5th root. Right. Okay, so the 5th root, yeah, I know what you're trying to get at. Yeah, you shouldn't have SQRT, but I know what you're getting at. It's the 5th root of x to the 4th. Yeah, you know what you're talking about. Yeah. Yeah, but I don't know how to represent 5th root. Just write out the 5th root of x to the 4th. Okay, now, first of all, let's consider domain. What's the domain of this function? That's important to note. All right. Well, are positive i's for x okay? Sure. Is 0 okay? Well, yeah. 0 to the 4th is 0. The 5th root of 0 is 0, so 0 is okay. What about negative numbers? Well, I can take a negative number, raise it to that. I get a positive number. The 5th root of a positive number is positive, and you are correct. Domain is all reals. I'll put my my bar there. I'm doing this because it's supposed to be double bar. So yeah, you're right. Domain is all reals. So that's the first thing, right? Remember, in order for a function to be even or odd, the domain has to be symmetric about 0. Here, that is the case. So it has a chance of being even or odd. It has a chance. So what do we do? F of x can be thought of as either this or as this. So what is it that we have to analyze? F of what? We have to analyze f of the opposite of x. All right. Anytime you do an even odd analysis rigorously, you got to do that. So let's plug that into here, the radical form. The 5th root of opposite of x to the 4th. What impact does the 4 here, the 4th power, have on that -1 factor? What happens?
becomes positive.
Correct, right. So you get the fifth root of x to the fourth. So lo and behold, all throughout the reals, look at this. F of x and f of opposite x, you get the same result. Is the function even, odd, or neither? The function is just like x squared, where if you're replaced with the opposite, doesn't matter. This thing is even. And here's the proof. Right, the proof is right there. I guess
so you just plug in the opposite and check the outcome.
Right, I guess I should say this equals f of x. Okay, so f of opposite x equals f of x for every x in the domain. Oh yeah, I know you're asking about this. That's to make it super legit for all x in the domain, not just 1 or 2 or 3, but all real numbers. Okay. All right, fill in the blank. The graph of y equals f of x is symmetric about. Okay, we have the graph of y equals f of x. It's an even function. We have symmetry about what? Y is a function of x. Even function is like y equals x squared. Graph is symmetric about the y-axis. Correct. Okay, just like y equals x squared, that bull, right? In fact, this guy, I think this guy's a bird beak. He's like x to the 2/3. He's a bird beak. Yeah, see that? Where the domain is all reals, we do pick up all real numbers as x coordinates. It is even. See, we have symmetry about the y-axis. Now, bear in mind, a lot of graphing calculators don't know how to graph these things. A lot of graphing calculators mess up. A lot of graphing calculators don't know how to graph the cube root of x. They don't know that x can be negative. So a lot of graphing calculators mess up. Desmos is better. All right. Okay, now for 2.
Since all exponents are odd, is that why it is odd?
Right, but for the proof, the idea is it's very similar. You want to analyze g of opposite t. So I'll take you through this idea. Work out g of opposite t. You're going to find it's the opposite of all this stuff over here. Okay, so you'll find that when you replace t with the opposite and work it out, you're going to get the opposite of that. I'll leave that to you. I think you'll get it, right? And then you're going to find that g is an odd function. Any questions? Okay, so you plug in the opposite of t, verify you get the opposite of this. Now, if you have y as a function of t, so t replaces x here, the graph of an odd function is symmetric about what point? What point? It's still the origin, 0, 0. I don't care if it's t.
There's no shift, right?
In the sense that it's got to go to the origin. Yeah, let's draw them, right? You know, Desmos is a great tool. T to the 5th plus t to the 3rd plus t. Okay, it's odd. It's apparently odd, right? Graph is symmetric about the origin, meaning that you have rotational symmetry, 180 degrees. Yeah. Bear in mind, if you had like a +1, that destroys it. That's neither. If you throw in a +1, +2, that's neither. Okay. But t to the 5th plus t to the 3rd plus t to the 1st, that's odd.
Horizontal shifts would destroy it as well, right?
Correct. Yeah, it typically would. In fact, give me a type of function where you might get coincidences. I'll give you a hint. It's later in the class. Can you think of a kind of graph where if you shift horizontally, you might get the same graph actually?
Like sine and cosine?
Yeah, maybe variations on those. Yeah, sine and cosine, right?
Secant, cosecant, and
right. Yeah, all the strict functions. Right. For example, y equals cosine of x. That's an even function, symmetric about the y-axis. But there are various horizontal translations. You know, if you adjust this by the period, it's the same graph, right? If you take the argument, if you add 2 pi, 4 pi, 6 pi, it's the same graph because these are periodic, right? Yeah. But you're correct that a horizontal translation would normally mess it up, right? Like if I do this, okay, yeah, that messes it up. Yeah. But never say never, right? I mean, with trig, you have these periodicities. Yeah. All right.
Also, number 4, real quick.
On this section, yeah. Why is it rare? Yes, I mentioned this briefly in the x equals y squared thing. Why is it rare for the graph of y equals f of x to be symmetric about the x-axis? Well, the only guy I know that does satisfy this is the zero function, maybe on various domains. See, here's the problem. Let's say I take a point on the graph, all right? If this graph is going to be symmetric on about the x-axis, if that point's on the graph, so does this point have to be on the graph. What's the problem? Right off the bat, I know this graph is going to fail what test?
Vertical line test.
Correct. This graph fails the VLT, which means that there's no way you have y as a function of x. In fact, the only function I know of this form that will have symmetry is basically the zero function, which is the x-axis. Okay. The x-axis is symmetric to itself, but beyond that, if you go a little bit away from the x-axis, you need a partner at the other side, on the other side, and you're going to fail the VLT. So that's the danger. If you go even a little bit off the x-axis, you get this shadow, right? This shadow point that'll make you fail the VLT. Right. So that's why in your basic pre-calc, we almost never talk about symmetry about the x-axis. Not if you have y as a function of x.
Okay, thank you.
Yes, you're welcome. Yeah. Yeah, yes, these are key concept questions, right? What's a function, right? The graph's got to pass a VLT. If you have y as a function of x, right? If you have x as a function of y, it's the HLT. Okay, good, good. Okay, now any follow-ups before I go on? I'll keep these marks here. I can save this. Any more follow-ups before I go on? It's 9:31, but I'll go on. Who is next? Let's see. Okay, Nick, 1.1, 16, 17. Those sound like domain questions. Very good. Yes, yes. Oh, yeah, yeah. Some of the harder domain questions. Yeah. All right. So I'll set these up and then let me know if you think you can get it from there. Okay, so let's see. Number 16. Let's do this. When is this real? This is real if and only if. Okay, take a look at the top. Radicand, right? The 2 minus 5x. We're taking the fourth root of that up on top. Okay, tell me what kinds of values 2 minus 5x can be. What can it be? What can it not be, right? Tell me about 2 minus 5x. When is it legal? Or, sorry?
Greater than or equal to 0.
Correct.
Because of the fourth root.
Correct. It's an even root. So this top part is real if and only if the radicand is non-negative. For right now, it's okay if it's 0. You can have 0 on top, right? The fourth root of 0 is 0. It's okay to have 0 on top. So based on the numerator, I know that one requirement is that 2 minus 5x must be non-negative, right? The 0 case is okay for now. And there is another restriction. The denominator cannot be what number? The denominator cannot be 0, all right? So when is this cube root guy 0? Okay, so I'll put this, and the cube root of x plus 1 must not be 0. When does this radical equal 0? If and only if the radicand equals 0. So this is not 0 if and only if the radicand is not 0. You can work with inequations in this fashion. You can subtract 1 from both sides. X is not negative 1. If this creeps you out, just work with the equation form and then negate. All right. So down here we have the cube root of x plus 1. We only have a problem if x plus 1 is 0. That is, if x is negative 1. That's our only problem from there. Now, some students might ask, can x plus 1 be negative? For example, what's the cube root of negative 1? Is that a real number,
1.
or was it?
Negative 1.
Correct. The cube root of negative 1 is negative 1. We can take the cube roots of negative numbers and keep it real, correct? The only problem is when x plus 1 is 0, correct? That's the only real value of the radicand that gives us trouble. And I've completely taken care of it over here. All right. So when you proceed, you want to solve this inequality and basically combine the conditions. Okay, so students, would anyone like me to proceed with this? We can, that's okay. Would anyone like me to proceed with this? Else I'll jump to 17. Okay, but again, we can come back to this. I'll save this. All right. Okay. Yeah, we're not done yet, but try to do it on your own. Okay. 17. Or just wait. Wait tonight. 17. All right. Okay, we have here a nice rational function. All right. The top's a numerator, not a problem. If your top's the top's a polynomial. If the top's a polynomial, there's no problem whatsoever. The domain of a polynomial function is assumed to be all reals, and this guy's on top. But there is a problem on the bottom if the bottom is what number in value? If this bottom is 0 in value. All right. So basically, this is real if and only if the denominator is not 0. Is not 0. But in the meantime, it's easier for us to solve equations than inequations. Let's consider solving, for now, solve the equation. I'll write it out. 3t squared minus 5t minus 2 equals 0. And you could use either the quadratic formula, or it turns out that old school factoring does work. All right. But you're going to find the zeros, the real zeros of the denominator, and remember, you have to exclude them. They're the bad guys. They give us a 0 denominator. So those are my hints. Would anyone like me to proceed? That's okay. Would anyone like me to proceed? Maybe you need help factoring this. Would anyone like me to proceed? I can come back. Okay, I'm not discouraging questions. I just want to encourage people to keep working at it, see if they can get it. All right, so again, I can come back, but oh, that's it for now. All right. So yeah, I can leave this as a challenge to you, but if you'd like me to work it out with you, that's cool too. So would you like me to continue with this, or okay, let's see here. 1.4. Oh, okay. A question here. Oh, okay. Well, here's the thing. Don't worry about the numerator, right? The domain is all reals. You don't have to factor the numerator. You don't have to factor the numerator because the numerator is a polynomial. It's legit for all real values of t. You only have to either factor the denominator or use the QF. You only have to find the zeros of the denominator, the real zeros, and those are the only exclusions from the domain of real numbers. All right. Later on in chapter 2, we will factor guys like those. You cannot factor this further over the integers. But let me go back to 1.4 now. Okay. Oh, any more follow-ups before I leave the page? All right. So let me go to 1.4. Okay. Again, I can come back. That's fine. Oh, wait, 1.4. That's ahead. All right. 1.4, 1F, and 2B. Sounds like Battleship. 1F and 2B. All right. Yes. Many students ask me about 1F. Yes. Okay. Now, first off, do you remember this? Y equals the square root of 16 minus x squared. Does that ring a bell? Does that ring a bell? Y equals the square root of 16 minus x squared. Well, let's ask Desmos. Y equals the square root of 16 minus x squared. Look at that. That is a basic graph. It's an upper semicircle. Before, we spent more time on root 9 minus x squared. This is root 16 minus x squared. The radius of the overall circle is 4. All right. So we begin there. Radius of the full circle was 4. 4 here, negative 4 here, 4 here. All right, so it is an upper semicircle. But wait, what are we doing? we're adding 2. What impact does the plus 2 have on the graph?
Is it up to?
Correct. Okay, so yeah, I'll just draw it down here. X, Y. This is, okay, so the endpoint here was at 4, 0. The endpoint here is at 4, 2, right? The 0.40 goes up to the 0.42. Likewise, over here, the point -40 goes up to the point -4, 2. We still have a semicircular shape in the middle. I'm going to kind of shrink this piece here. Lengthen this piece. So we get that. Pretend that's a semicircle. The y-intercept is no longer at 0, 4. It's at 0, 6. All right. So try to do a better job with the semicircle. But yeah, basically, those are the key features of the graph, right? The endpoints, and you can get the y-intercept easily. And generally speaking, if you can find intercepts easily, it's usually assumed that you're going to put them on. All right. Any questions about that? Any questions? The key thing was recognizing that was a semicircle.
From like a lookup table? Or
Oh
just
yeah,
intuitively?
oh yeah, it's from the gallery. Yeah, I know he looks different from the others, but I do count him as a fairly basic form. So on exams, for example, I would have asked students to remember the gallery of graphs, and the upper semicircles were some of them, right? So here's root 16 minus x squared. Here's root 9 minus, 9 minus x squared. Okay, that was a smaller semicircle, right? Here's y equals the square root of 4 minus x squared. That's a smaller
What if there's a plus x squared?
Oh, well, that would be harder. Do you mean this? That's a harder graph.
Inside of the radical.
Oh, again, that would be harder. Good question, though, and I encourage you to experiment on Desmos. So here's y equals, let's say x squared plus 4, right? Okay, that's a problem. I know him, right? I know him. You should know him. But what about y equals the square root of x squared plus 4? Well, I only know that the domain is all real numbers, right? Because x squared plus 4 is never negative, right? But in order to graph this, you'd probably need to know calculus. Now, one thing that helps, though, is the fact that you know the domain is all reals. It's an even function, right? Look at this thing. It's an even function. You do have symmetry about the y-axis. And as x increases over here, it appears that this is also increasing. So actually, you might have been able to guess at a shape like this, but it would have been a sort of a conceptual analysis, right? You would have had to observe certain features of this formula. But in a pre-calc class, I wouldn't have expected people to sketch this graph, except maybe, yes, the y-intercept's at 0, 2. That's okay. And the domain is all reals. Domain is all reals. X squared plus 4 is never negative. Domain is all reals. All right. Any questions here?
I'm good, thank you.
You're welcome, yes. And I do encourage you to experiment with Desmos. I think you'll get a lot from just kind of playing with these things, right? So root 16 minus x squared, totally fair. Root x squared plus 4 or 16, not as fair. It's fair for domain, right? In the sense that it's a trick question. It's all reals. But graphing this, no. In calculus, though, that would be fair. All right. Now, 2b, that's another involved one. All right. But let's do it step by step. In the beginning, let's graph y equals, what's a good basic guy? Y equals 1 over x squared. I do count that as a basic graph, even though I know back in your algebra classes, you didn't really know him well. But now I'd like you to know the guys like these well. Okay, now as x increases towards infinity, this thing's going towards 0. This piece here is going up, 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 up. All right, it's got past the VLT. And there is an asymptote. It's a VA. And there will be an HA as well. Now, here's a graph of y equals 1 over x squared in quadrant 1. You'll notice that if x goes out to a million, a billion, a trillion, the denominator gets huge, but the fraction gets very small. If you plug in x equals a million, that denominator is huge, but the overall fraction is tiny in value, right? It's kind of like a million versus 1 over a million. But wait a minute. Look at this function rule. Is the corresponding function even, odd, or neither? I'll give you a hint. It's either even or odd.
It's even.
It's even. Therefore, the graph is symmetric about what?
Y-axis.
Correct. So this graph appears in quadrant 1 and in quadrant 3. It's the volcano graph. Right. It will be symmetric about the y-axis. All right. And hey, folks, we're not even done yet. That's just the basic graph. How do we do this? Let's do this. Maybe I should have written him in blue, but all right. When you multiply the right-hand side by -1, so we have y equals the opposite of the original, what happens to the graph? What happens to it?
It's upside down.
Right, you reflect about the x-axis. All right, so then you get, draw it like this, still VA, always a VA on the y-axis. Well, so far, VA on the y-axis, VA on the x-axis.
So the asymptotes flip as well?
Well, both the x and y axes are asymptotes. We have an HA and a VA.
Oh, we're looking at the basic function. Got you.
Right. Or yeah, or it's upside down guy. Yeah. Oh, okay. So the upside down guy, that's going to go like this. It's also even. All right. Question so far. Question so far. Next, let's substitute x with x plus 3. Do I have room? Green. When I substitute x with x plus 3, what happens to the graph? There's a horizontal translation, but which way? Which way?
Left.
Good, because it's kind of surprising. People see the plus sign, they think right. No, it's more like a compensation. You go left. Right. So you're going to take this thing. We still have an HA at the x-axis, but our VA, our vertical asymptote, is now at x equals, whoops, x equals -3. Right. So the graph shifted to the left. And finally, and I guess I can show the answer. What does the plus 2 do? What does the plus 2 do?
Shifts it up.
Right. So here's my answer using software. Yeah, this over here.
Yeah, when I originally did this problem, I got the horizontal and vertical asymptotes, but I forgot about the volcano graph. I was just thinking of it as a regular rational where you have like one function in quadrant 1 and in quadrant 3. And so I couldn't see how only one side had flipped, but then this square function.
Yeah. So y equals 1 over x. Let's go to Desmos. Y equals 1 over x. That's in quadrant 1 and quadrant 3. It represents an odd function. The reciprocal function is an odd function. But y equals 1 over x squared in blue, that's a volcano graph. It's an even function. Right?
I had forgotten.
Oh, yes. Oh, yes, the exponent matters. In fact, in this case, we call the y-axis an even VA, an even vertical asymptote. Whereas for the red graph, it's an odd VA. It breaks apart up and down.
Interesting.
Oh, yeah, it's very interesting. Yeah, yeah. We'll talk more about this in chapter 2. In chapter 2, we're going to analyze rational functions more rigorously.
Thank you.
Oh, you're welcome. Yes. Let's see if there's 1, 2, C. Oh, yeah. Are you referring to number 4? Is that correct? Oh, 1.4. Okay. I guess that's this one here. Okay. So how do we graph? Well, let's go to Desmos. How do we graph y equals x to the 4th? Let's get a new. I should have gone Desmos at the beginning. All right. Y equals x to the 4th. All right. That's a bowl. It's not a parabola, but it's a bowl opening upward. What does the -1 do to the graph? Y equals x to the 4th minus 1 in blue. Translate down 1 unit. We do have a y-intercept at 0, -1. All right. But again, I encourage students to do this by hand. I would discourage using Desmos as a basis of work. If you wanted to check, that's great. It's great to play with Desmos, but work out the work as though you were doing an on-campus exam without technology, except a scientific calculator, maybe. All right. Okay. It's 9:51, but I'm willing to stay if you're willing. Any questions? And of course, both sessions next week we'll have some homework time. So we'll have some time on Tuesday, more time on Thursday for the chapter 1 homework. All right, 1.25C. Ah, yes. All right. Okay, the y-intercept's not so bad. Plug in x equals 0, you end up with 0, 3. The hard part is the x-intercepts, if any. Okay, we can replace f of x with y, right? To find an x-intercept, we set y equal to 0. All right. So when is a radical equal to 0? If and only if the radicand is equal to 0. Nine minus 3x minus 4x squared. All right. And again, in order to keep it real, we only take square roots of what kinds of real values? We only take square roots of non-negative values. Okay. All right. Now, there are a couple of ways you can actually approach this. Oh, wait a minute. Wait a minute. I was thinking a domain question. We're looking for x-intercepts, right? Equals. Equals. Sorry, I was thinking of domain for a moment. When is this radical equal to 0? If and only if the radicand itself is 0. Okay, yeah, I forgot. We're not doing the domain question. We're doing where are the x-intercepts? Those are the harder questions. We set y equal to 0. We set the function guy equal to 0. All right. Now, some people might reorder this and use the quadratic formula. Other people might add and subtract from both sides to get a nice leading coefficient out here. So I guess the question is, would you like to use the quadratic formula or would you like to use factoring? Since students are less used to factoring, Maybe I can try factoring. All right. 0 equals. Any questions? Any questions? Add 4x squared to both sides. Don't say move. Add 4x squared to both sides. Add 3x to both sides. Subtract 9 on both sides. All right. So we're looking for the real zeros of the function. All right. So we set the radicand equal to 0. All right. Here I'm arranging it so that I get a nice positive leading coefficient on the right. So I'm especially interested there's a positive leading coefficient. Whether it's in the left side or right side, that's up to you. All right. Now, it turns out, if you try to factor this old school, I don't think it does. It doesn't. The discriminant, I believe, is it negative? B squared. Oh, no, it's not negative, but it's a nasty positive integer. All right. Okay. So you have to use the quadratic formula. Okay. Now, would you like me to proceed with this, or do you have a question about applying the quadratic formula? Oh, okay. And I give you a hint that if the digits of an integer, a positive integer, if they add up to a multiple of 9, the integer is divisible by 9. If they add up to a multiple of 3, the integer is divisible by 3. That's good to know. All right. Were there any other questions or inquiries? Okay, so we're at 9:56. So here's what I'm going to do. I'll give you maybe 5 minutes to gather your thoughts. I'm going to come back at 10:02. All right, and then as you gather your thoughts, let me know if you have any additional questions. I'll be back at 10:02. Pause the recording. But again, if you want me to pause the recording, that's fine. How would you find the y-intercepts? Oh, you mean on this one here? Yeah. Oh, that's easier in this process. Basically, you plug in 0 for x. So when you plug in 0 for x, you get f of 0 equals root 9. You take the principal square root, right? So that's just the positive 3, right? Not the negative 3. So the y-intercept will just be the point 0, 3. The x-intercepts are quite more involved. Right, and the student's correct, yes. All right, 1.4 2D. All right. You know what? I think Desmos might be better because my sloppy drawing here. Okay, let's use Desmos. This will be fun. All right, on D. In the beginning, let's start with the basic graph of the cube root. Y equals the cube root of x. X is the 1/3, right? That's the lazy snake. A basic graph, the lazy snake, the S graph. That's the cube root. Now, what happens if I substitute x with x minus 2?
I shift 2 units to the left?
Ah, not to the left.
Oh, not to the
right. Right, yes. Gotcha. The sign surprises. Shift to the right from the green graph to the purple graph. Remember, substitution and the sign surprises. We shift right.
When we graph, we said do you have to have x and y values and then graph from that one?
Oh, you don't have to point plot. No. The idea is that you want to take a basic shape and just move them physically. The idea is to not do too much point plotting. Right, it's through transformations. Right. And finally, the +1. What does the +1 do?
Shift 1 unit out.
Yes. So the final graph is the graph in black. And you should note that the key point is at 2, 1. Because remember, the point on the origin, okay, originally the origin was the x and y intercept for the green graph, the original graph, okay? It now moves to the point 2, 1, because the idea is that we're shifting right by 2 units and up by 1 unit. So it's good to trace that point where the origin moves to.
Thank
Yeah.
you.
Oh, you're welcome, yes. Otherwise, that's the only interesting point. You wouldn't have to bother point plotting. In fact, the whole point, is that I want you to be able to intelligently transform graphs so you don't have to go to point plotting.
All right, excellent. Thank you.
Yes, you're welcome, yes. All right, anything else? Dinner.